Practical Bayesian Inference in Python, Hands-on Beginner Lesson. In this lesson, you will learn what Bayesian inference means and how you can apply it using real Python data. We will explore coins, datasets, and real-world example problems. Ready to get started? Let us dive in. Running the cell now. Setting up the notebook to hide warning messages. This helps keep our workspace clean. Import NumPy as NP. We set the random seed to 42 for reproducibility. Running the cell now. This initial code sets up the Python environment for the lesson by ensuring reproducibility with a fixed random seed and suppressing warnings to keep the notebook output clean. Although there's no visible output yet, these steps prepare you to consistently explore Bayesian inference without distractions from warning messages. This foundational setup allows you to focus on learning key concepts with clear, consistent results. What is Bayesian inference? Bayesian inference is a way to update your beliefs using data. You start with an initial guess called a prior and update it after seeing new evidence. This lets you make better predictions, even with small amounts of information. Running the cell now. Let us explore Bayesian ideas with a simple coin flip. We use randomness to simulate flipping a coin. We will flip a virtual coin 20 times. Each flip can be heads or tails. We record the results using numbers. 0 means heads, and 1 means tails. The print statements show all our results and how many tails we got. This gives us fake data to use in our Bayesian calculations later. Running the cell now. This output shows the results of flipping a coin 20 times, where 0 represents heads and 1 represents tails. We see the exact sequence of outcomes and that there were 7 tails in total, which will help us update our belief about the coin's fairness. This illustrates how we start with data, the flips, to perform Bayesian inference by counting evidence, in this case, the number of tails observed. Bayesian updating, estimating the probability of tails. Suppose you do not know how fair the coin is. You can use a prior guess for the chance of tails, then update with your results. Let us set up our first Bayesian calculation. Running the cell now. We use the beta distribution to set our beliefs before and after we see the data. Import the beta distribution functions from scipy.stats. Set parameters for a uniform beta prior, meaning all probabilities are equally likely. Count how many tails were observed in the coin flips. Calculate how many heads were observed by subtracting tails from total flips. Update the beta distribution parameters by adding tails and heads counts to prior values. Update the beta distribution parameters by adding tails and heads counts to prior values. Generate 100 points between 0 and 1 to evaluate the beta distributions. Calculate the probability density function values of the prior distribution. Calculate the probability density function values of the posterior distribution. Import the matplotlib plotting library. Create a new figure for the plot with specified size. Plot the prior distribution as a dashed line. Plot the posterior distribution as a solid line. Label the x-axis as the probability of tails. Label the y-axis as the density of the distribution. Add a legend to distinguish prior and posterior lines. Add a title describing the plot. Display the plot. Running the cell now. This plot shows how the initial uniform prior, dashed line, representing complete uncertainty about the coin's fairness is updated to the posterior distribution, solid line, after observing the coin flips. Notice how the posterior peaks around the observed proportion of tails, reflecting increased confidence in that estimate. This visual confirms the lesson's goal. Bayesian updating refines our belief about the coin's bias based on actual data. Try changing the number of flips or prior values and see how the posterior moves. Quick real-world example, medical test. Bayesian thinking is not just for coins. Doctors use it to update the chance someone is sick after a test result. You start with a guess, the disease rate, and update it with the test info. Running the cell now. We are going to consider a scenario involving a test for a rare disease. First, we note that the prior probability of having the disease is 1 in 1,000. Prior_disease is set to 1 to 1,000, representing this prior probability. The test correctly identifies 99% of sick people, sensitivity. And it has a 5% chance of showing positive even if the person is healthy, false positive rate. Sensitivity is set to 0.99. False_POS is set to 0.05. Our goal is to find the probability that a person actually has the disease given a positive test result. We calculate the numerator for Bayes' theorem, sensitivity times prior probability. We calculate the denominator, which accounts for true positives and false positives. We then calculate the posterior probability by dividing numerator by denominator. Finally, we print the chance of having the disease after testing positive, rounded to 4 decimals. Running the cell now. This output shows that even with a positive test result, the probability of actually having the disease is about 1.94%. Notice how the code combines the prior chance of disease with test accuracy, sensitivity and false positive rate to update this probability, demonstrating Bayesian thinking in practice. This highlights the importance of considering both the rarity of the disease and test characteristics when interpreting test results. Loading real dataset, Titanic survivals. Let us use a real dataset to do Bayesian inference. We will study the Titanic passengers and see how beliefs change about survival chances. Running the cell now. This comment indicates the start of the data setup section. We import the Seaborn library to access its functions. We load the Titanic dataset using Seaborn's load_dataset function. We print the shape of the dataset to see the number of rows and columns. We display the first few rows of the dataset to get an initial look at the data. Running the cell now. This output shows the Titanic dataset we just loaded, containing 891 passengers and 15 columns of information. Notice key columns like survived, P-class, sex, and age, which are essential for studying survival patterns. By inspecting the dataset shape and sample rows, we confirm the data is ready for our Bayesian inference on survival probabilities. Let us check how many people survived versus did not. This will be our starting belief or prior for Bayesian analysis. Running the cell now. Here, the code counts how many Titanic passengers did not survive, 0, versus those who survived, 1. Notice there are 549 non-survivors compared to 342 survivors, which sets the stage for understanding baseline survival rates. This helps us frame our initial beliefs before diving deeper into Bayesian inference on the dataset. We find the proportion of passengers who survived. This number becomes our prior belief for survival in general. This helps us compare groups later. Running the cell now. This output shows the overall prior chance of survival for Titanic passengers, calculated as the average of the survived column. Notice that about 38% of passengers survived, which sets our initial belief before considering any other factors. This prior is essential as a baseline for updating our beliefs using Bayesian inference. Instead of everyone, let us look only at young kids. We filter the dataset to ages under 10. We count how many such kids were on board. We also count how many survived. This gives us new evidence to update our belief. Running the cell now. This output shows that there were 62 Titanic passengers under age 10, and out of those, 38 survived. By narrowing the dataset to young passengers, the code helps us focus the Bayesian inference on a specific subgroup, allowing us to explore how age influences survival chances. Notice the key counts here, as they set the foundation for updating our beliefs about survival rates among children. We start Bayesian updating for survival rates specifically among young passengers. Set the prior beta distribution parameters to represent initial belief, uniform. Calculate the posterior alpha parameter by adding young survivors to prior alpha. Calculate the posterior beta parameter by adding non-survivors among young to prior beta. Compute the posterior probability density function using the updated beta parameters. Create a new figure for the plot with specified size. Plot the prior beta distribution as a dashed line. Plot the posterior beta distribution reflecting updated beliefs for young passengers. Label the x-axis as survival probability. Label the y-axis as density to indicate probability density. Add a title describing the plot's focus on Bayesian inference for kids' survival. Show a legend to distinguish prior and posterior curves. Display the plot on the screen. Running the cell now. This plot shows the Bayesian update of survival probability specifically for young Titanic passengers, comparing the initial belief, prior, with the updated belief, posterior, after observing the data. Notice how the posterior curve shifts and tightens, reflecting increased certainty about survival chances due to the actual number of young survivors. This illustrates the core lesson goal, updating beliefs using real data through Bayesian inference. Try it yourself. Change the age cutoff in the code above to compare survival for other ages. Which groups do you think had the best and worst chances of survival? Running the cell now. Let us do Bayesian inference to compare survival between males and females. We start a loop over the two groups, male and female. For each sex, we select only the rows for that group from the Titanic dataset. We count how many people survived in the current group. We find the total number of people in the current group. We calculate the posterior alpha parameter for the beta distribution by adding 1 to the number of survivors. We calculate the posterior beta parameter by adding 1 to the number of non-survivors. We compute the posterior mean survival probability from the beta parameters. We print the posterior mean survival probability for the current group. Running the cell now. This output shows the estimated survival rates for males and females on the Titanic, using Bayesian inference to incorporate observed survival counts. Notice that females have a much higher posterior mean survival, 0.74, compared to males, 0.19, highlighting a significant gender difference in survival chances. This connects directly to the lesson's goal of comparing survival probabilities between groups by adjusting criteria, helping you understand which groups were most and least likely to survive. Introduce the interactive section where the user can set their own prior belief. Prompt the user to input their prior guess of Titanic survival probability between 0 and 1. Calculate the alpha, success, parameter of the beta prior distribution based on the user's guess. Calculate the beta, failure, parameter of the beta prior distribution based on the user's guess. Calculate the updated alpha parameter by adding the actual number of survivors from the Titanic data to the prior alpha. Calculate the updated beta parameter by adding the actual number of non-survivors from the Titanic data to the prior beta. Calculate the mean of the posterior beta distribution, representing the updated survival estimate after seeing the data. Print the updated survival estimate rounded to 2 decimal places. Running the cell now. This output shows the updated estimate of Titanic survival after combining your initial guess, the prior, with the actual survival data. Notice how the code adjusts your belief by weighting your input with the observed number of survivors and non-survivors, resulting in a refined probability of about 0.39. This demonstrates how Bayesian updating incorporates prior assumptions and evidence to improve accuracy. Mini-project, Bayes for email spam detection. Suppose you receive emails and want to know if a message is spam. You know that 20% of emails are usually spam. If an email contains the word free, it is spammed 70% of the time, but only 10% of not spam emails contain free. Calculate your updated chance that a message with free is spam using Bayes' rule. Running the cell now. This sets up Bayes' rule for determining spam emails. Prior_spam is the initial chance that any email is spam. Prob_free_given_spam is how often free shows up in spam emails. Prob_free_given_not_spam is how often free shows up in non-spam emails. Calculate the top part of Bayes' formula, numerator. Calculate the bottom part of Bayes' formula, denominator. Divide numerator by denominator to get the updated spam chance. Print the updated chance that email with free is spam. Running the cell now. This output shows the updated probability that an email is spam given the word free appears, calculated using Bayes' rule. Starting from a prior spam rate of 20%, the presence of free increases the spam chance to 64%, reflecting how the code combines prior knowledge with evidence from the word free. Notice how this posterior probability helps us make a more informed prediction about the email's spam status. Best practices for Bayesian modeling. Carefully pick priors that make sense for your problem. Always check the effect of the prior and test with new data. Visualize your priors and posteriors. Try simulations to build intuition. Use Bayesian methods when you want to add extra knowledge or handle small datasets. Running the cell now. This comment reminds us to avoid being overly confident in Bayesian inference by using broad priors when data is limited. The print statement explains that if you have little data, it's better to keep your prior assumptions broad to avoid missing the true results. Running the cell now. This message emphasizes a key best practice. When you have limited data, choosing a broad prior helps avoid overconfident conclusions that might obscure the true parameter values. The intent of this code is to remind you that careful prior selection is crucial to obtaining reliable Bayesian inferences, especially when data is scarce. You can do Bayesian updates with more than 2 groups. The Dirichlet distribution is like a multi-category beta. Try this out for fun when you feel ready. Running the cell now. This message encourages you to extend Bayesian updating beyond 2 outcomes by using the Dirichlet distribution, which handles multiple categories simultaneously. Notice how this tip aligns with the lesson's intent to deepen your understanding through more complex examples and simulations. Exploring Dirichlet distributions helps you visualize and test priors when dealing with several groups, reinforcing best practices in Bayesian modeling. Challenge: apply what you learned. Imagine you roll a die 12 times and see 2 sixes. Use Bayes' rule with a uniform prior to estimate the probability of 6. How would your answer change if you saw more sixes? Try coding it below. Running the cell now. Instruction to fill in the code for the problem. Set total number of rolls to 12. Set the observed count of sixes to 2. Set the prior beta distribution parameters A and beta 1, uniform prior. Calculate posterior alpha parameter by adding observed sixes to prior A. Calculate posterior beta parameter by adding number of non-sixes to prior B. Compute the posterior mean probability of rolling a 6. Print the posterior mean rounded to 3 decimal places. Running the cell now. The output shows the posterior mean probability of rolling a 6 after observing 2 sixes in 12 rolls, calculated as about 0.214. This value comes from updating the uniform prior, beta 1, with the data, reflecting how our belief about the die's fairness shifts based on the observed outcomes. Notice how the code applies Bayes' rule correctly by updating the beta distribution parameters and computing the mean, reinforcing the lesson on Bayesian updating with binomial data. Practice using different counts. Please like or subscribe on YouTube if this was helpful. Recap what you just learned. How to set and update beliefs using Bayesian inference. Real-world applications for coins, medicine, emails, and data. How priors and evidence mix in real Python code. Visualizing Bayesian updates. Keep exploring and test your ideas on new problems. Running the cell now. Thanks for learning Bayesian Inference. Let me know your questions in the comments. Subscribe for more beginner guides on probability, statistics, and Python. Happy Bayesian learning! Running the cell now.